We're about to dive into the engine that runs our entire universe. And it's not a star, it's not some distant galaxy, it's really just three core ideas: work, energy, and power. Now, these aren't just words you find in a textbook. They are the invisible rules that govern literally everything. So let's break down what they really mean. Okay, let's start with a little riddle. What on earth could a speeding car, a falling apple, and one of those massive hydroelectric dams possibly have in common? I mean, they seem completely unrelated, right? You've got a machine, a piece of fruit, and a giant concrete structure. But believe it or not, they all share a fundamental secret. And that secret is, they all operate using the exact same universal currency. And no, it's not money, it's energy. This is the one thing that connects every single action in the cosmos. It's the transaction that has to happen for anything to happen at all.
So let's get into it. This currency of the universe. We're going to break down what energy actually is and where you can see it working all around you every single day.
In physics, the definition is surprisingly simple. Energy is just the capacity to do work. That's really it. It's the potential, the ability, it's the stuff an object has that lets it make something else move or change. And it mostly shows up in two main flavors. So, those two states. First up, you've got kinetic energy. This is the energy of motion. That speeding car we mentioned, it's full of it. And what's really important here is that little squared sign on the velocity in the formula. It means if you double your car's speed, you don't just double its energy, you actually quadruple it. Then, on the other hand, you have potential energy. Think of this as stored energy. That apple hanging in the tree has potential energy just because of its height. Gravity is just waiting to turn that potential into motion. Okay, so if energy is the capacity to do work, what is work itself? Let's look at how all that energy actually gets put into action. In the world of physics, work has a super specific meaning. You're only doing work when a force you apply actually makes an object move a certain distance. You need both the push and the movement. And that little angle bit in the formula, that's key. You do the most work when you push in the exact same direction the thing is moving. The more your push is off angle, the less actual work you're doing. And this leads to a classic physics trap. You can push on something with all your strength. You can get sweaty, feel exhausted, and feel like you've done a ton of work. But if that thing doesn't budge, from a physics standpoint, you've done zero work. Absolutely none. Effort alone doesn't count. And this is the perfect example. The source material points out that you and your friends can push against a wall all day long. You're definitely applying a force, but the wall's displacement is zero. It's not moving. And in that physics equation, any force multiplied by zero distance equals zero work. Simple as that. Work can also be positive or negative. Just think about driving a car. When you hit the gas, the engine's force pushes the car forward in the direction it's already going. That's positive work. It adds kinetic energy, you speed up. But when you slam on the brakes, the force of the brakes works against the car's motion. That's negative work. It removes kinetic energy and you slow down. It's all about whether you're helping or hindering the motion. So we've talked about energy, the potential, and work, the action. So what's the next logical question? Well, how fast can we get that work done? And this brings us to our third and final key concept. And that concept is power. Power is just the rate at which you do work. It's not about how much work you do, it's about how quickly you do it. A powerful car engine can do a huge amount of work in just a few seconds. And the formula couldn't be simpler. Power is just the work you did divided by the time it took you. And the unit we use for power, the watt, is of course named after James Watt. His big breakthroughs with the steam engine were all about finding ways to get more work done in less time, which is the very definition of increasing power. It's a great reminder of how these physics ideas literally powered the Industrial Revolution. Okay, we've got our key players: work, energy, and power. Now we're going to talk about the most important, most fundamental, and totally unbreakable rule in all of physics when it comes to energy. And I mean it. This isn't just a suggestion or a guideline. It is a fundamental law of how the universe operates, and we've never, ever seen it broken. Ready? Here it is, the law of conservation of energy. All it says is that in any closed-off system, the total amount of energy stays the same, always. You can't make energy out of nothing, and you can't make it vanish into thin air. All you can ever do is change it from one type to another. And this idea, well, it changes how you see everything. Let's make this super clear with that falling apple again. Right at the top of the branch, before it falls, it's not moving, so all its energy is potential energy from its height. Then it lets go. As it falls, its height decreases, so its potential energy goes down, but its speed is increasing, so its kinetic energy is going up.
Halfway down, it's a mix of both. And then in that split second right before it hits the ground, it has basically zero height. So all that potential energy has been converted into kinetic energy. It's moving at its absolute fastest. See? The type of energy changed, but the total amount was the same the whole way down.
So, where can we see these principles playing out in an even more dramatic way? Well, let's talk about one of the best examples in all of physics, collisions. Collisions are basically the perfect little laboratories for watching these rules in action. They force you to figure out where all the energy and momentum went before and after two things smashed into each other. And they really come in two main types. So here are the two types. In a perfect elastic collision, all the kinetic energy you had before the crash is still there after the crash. Think of two billiard balls bouncing off each other cleanly. But in an inelastic collision, some of that kinetic energy is lost. Maybe the objects crumple up or stick together. Now, that energy isn't really destroyed, right? It just got converted into other things, like the heat from bent metal or the loud sound of the crash. And there's this one special case with elastic collisions that is so cool it almost feels like a magic trick. If you have two objects with the exact same mass, like two billiard balls, and one of them hits the other stationary one head-on, the first ball just stops dead in its tracks, and the second ball takes off with the exact speed the first one had. It's like they perfectly swapped velocities. All right, so let's just pull this all together one last time. Energy is the potential to make something happen. Work is the action of using that energy. Power is just how fast you do it. And watching over all of it is that one unbreakable rule: conservation. Energy is never lost, it just changes its disguise. So, I'll leave you with this final thought. We know for a fact that energy is always conserved. But think about the gasoline in your car. Only a small fraction of its chemical energy actually becomes kinetic energy that moves you down the road. So, where does the rest of it actually go? Think about the heat pouring off the engine, the sound it makes. That's the law of conservation, happening right in your driveway.